Good day, I'm Dr. T and welcome to my dining room table. Today I would like to talk about chemical reactions. And in this video I want to start off by looking at three of the very common classes of chemical reactions that organic molecules do. This is not an exhaustive list. In fact, in a later video I'm going to go into a couple of other types of chemical reactions. I'm going to go for kind of a generic look at them and then give a couple of specific cases for these. So let's start out and let's look at the first one. Okay, so one of the common organic reactions is that of the addition reaction. Addition reactions are going to start with an alkene or alkyne. You have to have a double bond. And what we're going to do is we're going to take some other constituent and we're going to add that to the double bond. So in this case, we'll have, effectively something that's, R and R prime. These can be anything. And I'll do a couple of classic examples for what this is. So now we're going to add those together. Those are going to hop onto the double bond. Actually, we can look at this by using what we call electron pushing. So I can say, okay, these electrons from the double bond, those are going to interact with one of my two parts of my molecule. It does very much depend on exactly what part of my molecule this is. This part needs to be something that will attract electrons, that wants to attract towards them. Okay, so as they attract towards, and we'll quite often call this an electrophile, but typically in this case, it's usually a hydrogen most of the time, but not always. So we're going to go ahead, we'll attract those, and then we're going to go into a intermediate step. My first R group has attached. Remember, R is just a generic term for thing, a part of a molecule. Very, very vague description as to what it is. I still have my R prime left over, and at this point it is almost certainly going to be negatively charged because these electrons have probably popped over there. The two-headed arrow indicates that two electrons are involved. If it looked more like a fish hook, that would be one electron. And in a later video, I'll discuss radical reactions, in which case those have fish hooks, because those are one electron at a time reactions. But for now, we're dealing with two. So that guy is going to be negatively charged, and this guy is going to be positively charged. This is a carbocation. This is a reactive intermediate. It is something that if you had it in, a vacuum of space or something, it could very much exist. It's not a transition state, which even in the vacuum of space would break down. But it is something where as soon as something hits it that it would like to react with, it's going to react, and, well, that R prime is going to be over here. So, boom, that's going to react, and this gives me my product. And I've added this to my molecule. So let's look at a couple of examples of this. So I can set things up fairly similarly. A classic reactant, I'm going to put it over the arrow. This is quite often done in organic reactions to indicate that I'm adding this to it, but I don't really want to try and follow it too closely. Quite often, it's just kind of a pain to deal with, and I might have multiple steps in this process where I'm doing multiple organic reactions, and I want to focus on the carbons. So in this case, I've got hydrogen. I'm going to need a catalyst, and that's going to be platinum. I could use nickel or palladium, I believe it is. And in this case, with that catalyst, which I believe I have talked about in a different video for one of my other survey classes, I am going to be adding those hydrogens onto that double bond. This is called hydrogenation. So if you see hydrogenated vegetable oil, yeah, that's this. But hey, here's hydrogenation. This is done because unsaturated fats, which are ones that have double bonds in them, are typically liquids, but sometimes you want a solid fat, but you don't want to go from an animal source. Instead, you want a plant source. Okay, let's go for another example. So I could have this guy. And because this one's not using a catalyst, it's not quite as complicated, because this catalyst actually will make this into a multi-step process. That's the whole point of a catalyst. So in this case, I'm going to do HX addition. X is a generic halide, so this would be chlorine, bromine, fluorine, iodine, etc. Usually, we're not usually talking about fluorine. He does behave a little bit differently, but it is possible that this would be a fluorine. Although usually you'll see this is like a bromine. Okay, so in this case, what's going to happen, and I'm actually going to go ahead and I will draw out where the electrons are going. So I've got this guy. The electrons are going to attack, and notice how I always put a squiggle on that line. It's a squiggly arrow that is indicating the electrons. So the electrons from the double bond are going to attack my hydrogen, and then the electrons from the bond between the hydrogen and the halide are going to go to the halide. And I'm just going to get rid of that because I'm going to do this as 2 steps. Then at this point, the hydrogen goes over here, the carbocation goes there, I have the X minus over there, and then it is going to attack, and now I'm going to get this guy. Now, what am I trying to write? There we go, there's the X. Now, when we have this carbocation, this is actually a place where we can get some really interesting chemistry taking place because it's a very reactive intermediate, and thus we can get things adding on to it that we weren't particularly planning on, so I can get unintentional products. Also, I can get things like rearrangements. So potentially, if I had, say, a molecule that was like this, and if there was, say, another hydrogen on here, say a hydrogen that was hanging out on this carbon, that hydrogen can actually move over. The whole thing shifts carbons, and therefore I can end up getting obviously I'm not drawing all of the carbons, but I can end up getting, don't need the X yet, the carbocation moved, and as such, see if I can draw an X. As such, I can get my product to be something slightly different. Say, so now there's my H. And I can end up getting my addition happening on the wrong spot. This will happen depending on what my configuration of my molecule is. Different reaction conditions, different chances of this. But you can start getting some interesting stuff, including my complete inability to draw 5 carbons over there. Okay, so that is addition. Actually, there's one more I want to show you on the addition reactions. Okay, so for the next one, what I'm going to be doing is looking at a hydration reaction. So in this case, I'm going to take my double bond, and I'm going to react it with water, but I'm going to write it a little bit oddly. I'm going to write it like this. And this H is going to be acting like an electrophile, one that's attracting electrons, or is attracted to electrons. And the OH is going to be acting like a nucleophile, one that's attracted to nucleuses. And we're going to see how that plays out here shortly. It's exactly how you expect it will. Okay, so the attack starts. One of the bonds from the double bond attacks the H. The electrons from the H-OH bond go to the OH. And then we get ourselves our intermediate, which, as the other ones, is a carbocation. And we have our OH minus hanging out over here. Now, this guy attacks there. And we get ourselves an alcohol. And this is one way to get yourself an alcohol. If you want an alcohol, if you start out with a double bond, you can get yourself an alcohol. Works good. Okay, so next up, I want to show you one where instead of having a hydrogen acting as the electrophile, it's somebody else. So let's look at this guy. And this is a test we can actually do for double bonds because the reagent that I'm using, the Br2, which is going to be 2 bromines hooked together, this guy is actually kind of reddish in color. So if this reaction takes place, then the reddishness will go away. So this is going to happen basically like the others. This is going to attack over here. That's going to go to there. I'm going to get this guy. One of those lone pairs is going to attack. And then I get bromines on my molecule. And thus I've brominated it. So yeah, that's addition reactions. This video is getting rather long, so I'm going to break this into a couple of parts. So that's addition reactions, and in later videos I will cover elimination and nucleophilic substitution. But until then, have a wonderful day.